So for today, we are going to be looking at how quantum mechanics, which is what we talked about, I guess, 2 times ago, how quantum mechanics applies to the physics of the atom. So this is not the physics of the nucleus. We'll get to the physics of the nucleus later. This is the physics of the atom, and gives us an idea of, well, it tells us how atoms are put together, what shapes they kind of have, and how they bind together, and explains why we have the periodic table the way that we have the periodic table. So that is the plan for today. We are going to be looking at this textbook at some units. The units we will be looking, or the chapter we'll be looking at, is chapter 30. So the discovery of the atom, discovered the parts of the atom. Okay, so we discovered atoms. We discovered that the atom had parts, like a nucleus and a proton is the neutrons and electrons. I assume everyone already knows that. Bohr's theory of the hydrogen atom, which is wrong. And then, what's that? Atomic origins. Applications of atomic excitations and de-excitations, that's going to be useful. Wave nature of matter causes quantization. That will be really interesting. That's actually probably the most interesting part of this thing. Patterns in spectra reveals more quantization. Ooh. And quantum numbers and rules explained in the Pauli exclusion principle. No problem. Seems pretty good. Okay, so we have this thing, quantum mechanics. Quantum mechanics states that particles are waves. Particles satisfy the wave equation. And because they are waves, they must satisfy all the boundary conditions associated with being waves. And they interfere with each other the same way that waves interfere with each other. So let's assume that we have a wave in a single box, a one-dimensional wave in a single box. So that would look something like this. I have these walls here. This is a potential. We've talked about potentials in the past and how the potential tells you what the energy is. So this is the potential, and it goes up to infinity on both these sides. So this is called the infinite square well. So it's flat, you have a constant energy down at the bottom. It could be 0, it could be whatever you want, because energy, remember, is just a function of wherever you choose your origin to be. But these then go up to infinity up in this direction. And so then you have a wave that you need to fit into this box. So the only waves that fit into an infinite square well means that it's impossible for something with finite amount of kinetic energy to drive up this hill. So let's say that you have a hill that looks more like this. So you have a smooth potential, and this will be, so like, in this case, it'll be like a nuclear force, but it could be an electromagnetic force. It could be, whatever. It could be a gravitational force. You have some amount of kinetic energy of your particle. It will roll up this hill up to the point where the kinetic energy is dissipated, and you have only potential energy left, and then it will roll back down. So you can climb up this hill and penetrate into the barrier by some depth. In other words, well, if this penetrate to where the potential is rising. Here, this goes from basically no energy to infinite energy directly, and so there's no height where this thing will roll. There's no penetration depth where this wave, as it's bouncing back and forth, will fit in the sides. So it has to go directly to 0. The probability of detecting this particle, in other words, the probability of the wave having some amplitude outside of this barrier, is 0, because the potential goes up to infinity. So that gives you a set of states. These states don't necessarily stack on each other, but we're going to put energy up here. So in this space now, they do stack on each other, where energy is upwards like this. So the higher the energy, and then we're going to look at what states you can form. Well, you have to have states that go to 0 at the boundaries. Here's a question. Why does radiation break down our cells or our atoms? So the radiation from any of these things comes out with sufficient energy to break the bonds that form like DNA or lipids or whatever, because they're all pretty small. Okay, so here we go. The lowest energy wave that you can fit into here is one that looks like this. The next highest energy wave that you can fit is one that has an additional bump in it, like that. The next highest wave that you can fit, it has to go to 0 on the boundaries. That's the thing. So it satisfies this condition where at this point and at this point, the probability goes to 0, like the relative probability goes to 0. So the energy here doesn't go to 0, but the amplitude of the wave goes to 0 at both of those things. All right, so then you can have one that has 3 bumps in it. So that would look like this. You can have one that has 4 bumps in it. Kind of. I did my best on that one. All right, and 5 and so forth. So you have a set of waves that will fit into this box, where you have a wave that bounces back and forth, has to satisfy the boundary conditions, and so these are the waves that you get. It's the same thing with the musical instruments, the same thing with a guitar, it's the same thing with an organ pipe. You have certain states that will fit into the pipe, and that produces the overtones that give the musical instrument its timbre. So the same thing is true here with, say, an electron trapped in a square well, or a nucleon trapped in the square well of the nuclear forces. Okay, now what? Well, so each one of these is going to have its own energy. You can jump from one state to another, but you can't jump to any intermediate state because there's no intermediate state to jump to. Like you can have your wave function wiggling, oscillating at some frequency. You can jump to some higher frequency, but the only higher frequencies that will survive in this chamber are ones where it fits within the boundaries that you have. And that quantizes the system. And that's the thing. This is what produces the quantized states. This is what produces the different energy levels, is the fact that only certain wavelengths will fit inside your potential. Okay, so these are the quantum states for an infinite square well. Now let's take a look and consider what happens when you're talking about a nucleus. So with a nucleus, you have a different kind of potential. The potential of the nucleus is 1 over r potential, so it looks, so here's like potential energy here. It's going to look like this. So this is what the potential looks like. And then the question is, and this is going to go in all directions, right? So here's a two-dimensional slice of this three-dimensional thing. And so you're going to build up some wave structure inside this potential. Okay, and that wave structure is going to depend upon the nature of the force. Well, the electromagnetic force, the potential for the electromagnetic force, squiggles is not equal to, squiggles, 1 over r. And it's q over r is depending on, so q over r, I guess we'll do it. Q, this is a q, not a g. Q over r, this is the charge of the nucleus. All right, so the nucleus creates this situation, and now the question is, it creates a situation where you have a potential that can trap something. But the question is, what are the boundary conditions that you have? So for the case of that infinite square well, we had the boundary condition that the amplitude had to be 0 at both walls. So it didn't matter what wave you put in here, it had to go to 0 at both walls. For the case of something that looked like this, where it's a force that only exists in some radial direction from it's a field that exists only in a radial direction from your source. So this is a source charge. The electromagnetic field is radial in all directions because of that. So this has to also satisfy a wave equation. The question is, what do these waves look like? What are the boundary conditions that constrain the properties of this wave? There are 2 boundary conditions. The number 1 boundary condition is, so here's your 3 axes, x, y, and z. Looks like, oh, that was bad. X, Y, and Z. Come on. Yeah, that was pretty close. So we'll go with that one. One of them is, if you start here and you wrap your way around like this and get back to there, you have to arrive at the same value. So it has some probability. The electron has some probability. So again, here, the situation is you have a nucleus made with neutrons and protons. That's going to create an electromagnetic field that goes as 1 over r. So here's your nucleons down here. Here's this 1 over r field. And now you have electrons that you're going to throw into this pit or into this box, and they have to satisfy the wave equation as they are in the vicinity of this material. So the question is, what waves fit in a 3-dimensional space given this shape of the potential around that space? If it's a square well, you get these ones, these sine waves. For this one, you have different boundary conditions. One of them is whatever the value of the wave function is here, which it means whatever the value of the probability here, when you go around 360 degrees from the pole back over here, you have to have the same value. You have to arrive at the same value. So it doesn't have to be 0, but whatever it is, you have to match it in the end. And I think you also have to match the derivative because it has to smoothly vary. You can't have, there's no reason why this direction is more important than that direction. Like these 2 directions are the same. And so it has to smoothly vary as you rotate your coordinate system. The other thing that happens is that if you start here and you rotate around this direction, so you're rotating around this axis, starting from here, going around this horizontal plane, you arrive back, and the same thing has to hold here, that you have to arrive at the same value with the same derivative at that location. So those are two boundary conditions, and the question is, what waves can you fit in a sphere? It has to be a sphere because it only depends upon the radius. If you have a force that only depends upon radius, you can only make spheres out of it. So gravity, the reason the Earth is round is because gravity only depends upon distance, and therefore you only make spheres out of it. Okay, so you have to have a wave equation or a wave that fits into this volume that matches these boundary conditions. That the amplitude and the phase basically have to match up at 2 pi here and at 2 pi there. Okay, and one of these is going to be the z-axis. Usually this is the z-axis, and you measure the angle from the z-axis it's the angle theta. This one here is the azimuthal axis, which is a rotation around the z-axis. So in this case, it's a rotation around either the x or the y-axis or anywhere in between. And for the one that's in the plane, it's a rotation around the z-axis. This is usually given by the Greek letter phi. If you're a mathematician, they often do it differently. They'll have theta be the one in the plane and phi be the one from the pole. But this is a physics class, and so we're going to do theta from the pole and phi from the plane. Okay, once you do that, you say, okay, whatever wave I have that's going around this thing, it has to match at these different boundary conditions. What are the possibilities? Well, a simple possibility is that you just have a wave that starts at the origin. So here's your probability wave, and it expands and contracts. So it oscillates purely radially. If it's a pure radial oscillation, then every point is the probability or the amplitude at every point is going to be the same all the way around that sphere. So it's going to oscillate like this, and it's going to create a spherically symmetric energy state where your electron can live around the nucleus. Okay, so we should look for those. Well, that's going to be this up here. Right, so these are examples of waves that are spherically symmetric, these two at the top. Spherically symmetric waves, it corresponds to oscillations in the radial direction only. Now, these are probability oscillations, oscillations of the amplitude for the probability of the electron being there. They are not, this is not the electron actually breathing in and out around this thing. It's the probability of detecting an electron around this nucleus is oscillating with, and it forms these kinds of patterns. So that's these two up here at the top. You can also have a situation where, say, let's just look down at the azimuthal plane. So we're looking down the z-axis, and we've got like x and y here, and we want to say, okay, I'm going to start here with, say, some probability, and then that probability is going to decline, and then it's going to expand again, then decline, and so you get this kind of peanut-shaped thing, where the probability goes down as you go around some direction. The probability is going to go down somewhere and then back up on the other side. So this is, you start from spherically symmetric, which would look like this, and then you go to this one where you get kind of a figure eight. Or you could also say it comes up like this, goes through the origin, and you get two loops as you go around. Okay? And if you can do that around this axis, you can also do it around this axis. So you get that one, and you can also do it around this third axis that would come into and out of the vort. So you have like 3 different dumbbell-shaped things. Well, that's these ones right here. So that's this and this. And where's the other one? They're not showing the other one. But anyways, you get probability densities that look like this. Okay, well then you can have, what if I wanted to have, here's this 2 planes, and I want to start here, and I want to have 2 bumps in it. So then you can get something that goes, as I rotate around, it's going to go, what, like this? Like that kind of wave. Well, that's going to show up right here. So see that? How amazing that is? Okay, and then it's like, okay, now I want to have another loop in it. So I'm going to draw this. I'm going to start at this location. And remember, these axes are arbitrary. They can be in any orientation to start with. So then I can do, okay, now I need to do something that's going to look like this, I think. Oh, did I do it right? I don't think that that's quite right, but anyways, you get the idea. So now I've got these 2 lobes that are in the middle here, and that looks like, where is it? Something like this. Okay, so that's around one axis, but then you also have the vertical direction as well, and so you get the same kind of structures in the vertical direction, and that sets up all the different waves that can fit around the nucleus, and you get these structures. Okay, and what happens is for each of these structures, so these are called the spherical harmonics. This is what the formula looks like to give you the probability density, right? So this is the amplitude, this psi here. This amplitude is, there's a whole bunch of square root things. That's to make the probabilities come out to 1 when you add them all up. And then you have this e to the rho thing. So that is the radial direction. Rho is the radial direction. It should be r. Yeah, so that should be r, but it's not listed as r. And then you have these YLMs. The YLMs are the radial. So the radial direction, like from the center, is that first part, and then the YLMs are the azimuthal, like the angular directions around different rotation axes. Okay, and so you get these these shapes. And then the final thing that's important is that electrons are called fermions. They obey the Pauli exclusion principle, which means that no two electrons can occupy the same quantum space at the same time. No two electrons can occupy the same quantum state at the same time. And so the states are, what are the numbers that describe, or what are the labels that I can assign to these different possible states? Okay, so let's go back to the infinite square well because it's a little bit easier to draw. So I have this state here. That is one quantum state. How do I describe it? I describe it, however I want. I can describe it as like the number of bumps that it has. So this is n equals 1. The next one above that has 2 bumps like this. And so this one I will define as n equals 2. And it's a good reason, there's a good reason to define them with integers that are consecutive, because then you can determine the energy associated with each of these states as a function of what this n is, and then it can be useful. So, and then this will be like the n equals 3 state, which would look like this, although a little bit better drawn. So this would be n equals 3. So these are quantum states. These are quantum numbers. They tell you what state you're in. So for the case of a one-dimensional infinite square well, these are the quantum numbers that you get. And if you were to put electrons in this box, so I'm going to stack in some electrons, the Pauli exclusion principle says that no two electrons can occupy the same quantum state at the same time. So I throw in an electron, it's going to come and it's going to occupy this ground state. If the temperature is low enough, the ambient energy of the electron is low compared to the gap in these energy levels. So there's going to be some energy here, some change in energy. And if the temperature of the electrons as they come in is small compared to these things, then they don't have enough energy to jump between the quantum states. They'll settle to the ground state. Okay, so here's the ground state. I throw an electron in, it's going to be like this. If I throw a second electron in, it would not be allowed to go into the same ground state. It would have to go into the first excited state, except for the fact that electrons have their own intrinsic quantum numbers as well. So the electron has its own intrinsic quantum number, and so when you put a second electron in here, it will occupy this state because now it can have there is one quantum number left to it that it has available that can be unique from the other electron that's in here, and that is the spin. So you can have one that is spinning upwards and one that is spinning downwards. Or it could be spinning to the left and then the other one to the right. Either way, as long as these two spins are opposite each other, each one can have a unique quantum number. In particular, it's in the n equals 1, s equals plus, or the n equals 1, s equals minus. So that would be these two quantum states. So the quantum states are, we give them numbers, but those numbers represent the physical situation that's going on there. It's a way of calculating what it is. So now you have, if you put a third electron in, it won't be able to fit in these states, and it will go up to the first excited state. So the first excited state, you can have one electron that goes in there, and then you add a second electron, and it would come in like this. And again, it doesn't have to go into the spin up state first. It can go into either of the states, as long as when you add the second one, it will go into the opposite state, so that each electron has its own unique quantum number. Well, that's what's going on here with these electron orbitals, is that when you have the spherical shell of an electron orbital where the wave is a radial, it wiggles in the radial direction, the oscillations are in the radial direction, then you can have two electrons that occupy that energy level. The different quantum numbers that you add to the system are the ones that count the number of bumps that you have in the different directions. And so you have the n, which is the number of nodes, basically like what energy level is it, how many oscillations are there in the radial direction. So n is, that is usually given, quoted as the energy quantum number, energy. And then you have the L and the M quantum numbers. These are the angular momentum, and then M is called like the Z projection, LZ, the angular momentum projected onto the Z axis. But this actually corresponds to how many bumps do you have around the azimuthal direction. So if you're looking down the Z axis, okay, and you have some amount of angular momentum that you have to have. So the amount of angular momentum that you have to have is how many nodes or how many oscillations do you get as you go around the circle. How many oscillations do you have in this direction, like that? So this one has 2, for example. And one of those other ones, the one that I drew that was like this, that has 4. Well, okay, it's got 3. It's got this one, that one, and this one. So when you add another node to the system, then corresponds to some amount of angular momentum that's available to you in that system. So that angular momentum can be partitioned between the x-axis, the y-axis, or the z-axis. And so this quantum number here tells you how much that momentum is projected along the z-axis, or it's used to characterize the amount of angular momentum that's projected along the z-axis. Okay, so L is the total angular momentum of the system, or the angular momentum of the electron as it goes around the nucleus. M tells you how much of that angular momentum is oriented in the z direction. And it's a mathematical direction that we assign because that's the coordinate system we want to use. Okay, and so the projection in the z direction can be however much angular momentum you have. You can either put it all in the z direction, or all in the minus z direction, or anywhere in between, as long as it produces an integer number of nodes in the wave that's propagating around, because all these electrons satisfy the wave equation. So what you end up with is that you have the amount of angular momentum that you can have is limited by the amount of total energy that you have. So energy can be some value. The angular momentum has to be less than the amount of energy that you have, but still greater than 0. You can't have negative angular momentum in this case because it's the nature of the mathematics doesn't allow you to have it. And then M can be anywhere between and equal to minus L and positive L. And that's just a way of numerically assigning numerical values to these different shapes. These are the shapes that you produce when you satisfy the wave equation that applies here, to the electrons as they go around in this electromagnetic potential. These are the solutions to that wave equation. The solutions are exactly the same kind of solutions as what you get for a jump rope attached between 2 walls. And then you assign numbers to each of the allowable states, and those numbers are the quantum numbers, N, L, and M. And then you have the spin quantum number that is the last piece of the pie. So all of these things together are going to be what produces the periodic table of elements. So if I come here to P table like this is the periodic table of elements. And you've got, what am I looking for? Properties. So you have these different shells that we described. We have the spherically symmetric shells. So spherically symmetric shells look like this. Let me get a different version of these shapes, one that actually, so these are some of the higher order shapes. I want to get one that's a lower order shape. So let's do this one. Okay, I want to use this one because this one actually starts at the ground state. So you have this ground state right here. That's the lowest energy state. And you can put 2 electrons in it. Okay, there you go. 1, and then 2 would be helium. Okay, if you go to then the next higher radial direction, so that's a single mode pulsating in the radial direction or oscillating in the radial direction. If you have a node in that direction, so for example, if I plot the radial direction, if you have something that looks like this, here is the radial direction. I have a wave. If my wave looks like this, okay, like that, that's the ground state. That's the least excited state that I can have. This is the probability density. If I have something that looks like this, like that, then that is the first excited state. You'll notice that I cross this thing here. So I've got a set of nodes in the radial direction. And then I can have another one. I can have one that goes through 0. I can have one that goes like this. Okay, so that would be another one, but all of these different modes have different energies. There's a different energy associated with each one. Typically, you'll only get something 0 probability in the center when you incorporate an azimuthal mode, like the waves propagating around the equator of this distribution. So if we're just talking about the radial modes, then it doesn't go through 0. If you're just talking about the radial modes, then you only get these things that go like that. So there's one that has an extra bump in it, and then I can draw one that has even more bumps in it, like this. Okay, so all of those, that should go above. Anyways, all of these different vibration modes are the different, each one is the next highest energy in that thing, or in that tower. Just like we had the tower of allowed energy states, each one of these radial oscillation modes is a new energy state. Each one of those, if it's spherically symmetric, is going to have its own pair of electrons that it can contain, and these are all spherically symmetric, which produces the S shell, and that's all of these things. So everything in these first two columns are ones that have their outermost electrons are in this S shell. Okay, so then you go to the next excited state, which looks like this, where you have this one lobe in each direction, and you can have 2 electrons in each of those. So that gives you 2 for this direction, 2 for this direction, and 2 for this direction, which gives you 6. 1, 2, 3, 4, 5, 6. So that's the P shell. These elements over here all have their outermost electrons in the P shell, which means all their outermost electrons are in shells that are shaped like this. Okay, and then you can have 2 in each. Okay, and once that shell is completely filled, then you're up here. This is that. So a full S shell gives you these ones. A full P shell gives you these ones, the noble gases. Helium is stuck over here, even though it doesn't really deserve it. Helium is stuck over here because it doesn't have enough electrons to actually fill out any more excited states in the P shell, at least not when it's in its ground state. So this is all formed when these elements are in their ground state. When you start exciting them, then the electrons can jump into other energy states, but their valence electron, when they're in the ground state, is going to be in one of these shells. Okay, so the next one, the next shell that I wanted to look at is this one. So this is the next highest one. It's got 2 lobes in each of the directions. So this one has 1 lobe. Okay, so this one has 2 lobes. This one has 4, which is an extra node in the system, right? This is the one, I drew this one already. So these are the different ways you can arrange it. You can have them go around this direction. You can go around that direction. Then you can have it go around this direction. Then you can have this one, which is different from this one, because you'll notice that the pink is a different location than the blue. And then you have this one here in the middle. So these are the +2, or like each one of these allowed energy states, angular momentum states in this energy level, is going to have 2 electrons that are allowed in it, which gives you a total of 10 electrons, where the outermost, 10 different ways of adding electrons to a system. Let me try that one more time. Here we go. You can hold 10 electrons in these energy states without having them overlap each other. Okay, so that gives you 10 elements. You can fill up this shell here with 10 electrons, which gives you 10 elements to burn in that shell, and that looks like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these transition metals correspond to having an outermost electron in one of these states, one of these waves. And then this one here, that's the last one. It's not the last one. You can have an infinite number of these things. It's just that we run out of stable nuclei to support them. So this last set down here has 7 allowed angular momentum states. So this is 7 allowed waves to propagate around the different axes that we have and the different angles that we have. So that should give us 14 different elements, and we will notice that in the periodic table, these things down here, there are 14 elements that run along these things. So 14 elements, they're the lactinide series, or lanthan something or other series, and actinide series. These are all elements whose outermost electrons live in one of these energy states. So there we go. There are some questions here. Is all this theoretical or verifiable? This is all verifiable. And the periodic table shows that this is verified. So you do the math, you say this is what quantum particles have to satisfy this equation and these boundary conditions. That gets you a set of solutions. Those solutions are these spherical Bessel functions, YLM. They're not really important for our purposes today, but they're there. So these are the allowed waves that you can fit in the box created by the nucleus, the potential energy box created by the nucleus. These are the waves that fit inside of it. And so then you just enumerate those waves that fit. You classify what the waves are depending upon their symmetries, whether it's spherically symmetric like these ones, or whether it's got 2 bumps or 3 bumps or 4 bumps or 7 bumps or whatever. And then you get 2 electrons in each of those. And then the experimental verification is here in the periodic table. But you can also see how they bond together. You can do calculations to show how the hydrogen bond should form, for example, in water. So these things signify the states. The numbers themselves just enumerate what are the different states that I'm talking about. So this would be the n equals 2, L equals 0, m equals 0. This is energy is 2, this is the second excited state, so this is also the second excited state, or maybe so this would be the first excited state. So the smallest number you can have here is 1. So this is the first excited state, this is the second excited state. The other one would be the 0, the first, like the ground state. And then 1, like here's this 1, and then here's a 3-1 and the 3-1-1. This just tells you how you distribute the angular momentum around the nucleus. So these are NLM. These 3 quantum numbers are NLM, and then they fit into this with NL and M. Okay, so this YLM corresponds to a specific combination of polynomials and trig functions of these 2 variables. So these quantum numbers are ways of specifying which of these orbitals you're talking about, and then you put the electron in it, and then you win. Let's see. Before, what about the bottom loop? Sorry, that one, I missed the time when that happened. Okay. Is it ever possible to have negative angular momentum in these states? No, because you're given, it's the absolute value it's the square root of the absolute value of the angular momentum squared is what you're given. The Z projection, so you say there's a total amount of angular momentum in the system, and then the third quantum number, which is the M quantum number, that third quantum number is related to which direction that angular momentum is pointing. And so there's a total amount of angular momentum that you have, and then there's which direction does that angular momentum point is the third quantum number. So they all have positive sign. The angular momentum, just absolute value, is the second quantum number. The third quantum number is where is it pointing. And that is what's given there. And then the spin is the last one that comes in. That in this case, you don't include it because the spin isn't part of the wave equation. The spin is a property of the electron itself. Okay, so that gives you there you go. That's all of chemistry. Everything you need to know about chemistry right there. See how much better physics is than chemistry? You just you solve this wave equation, and there's all of the periodic table just explained right off the bat. Okay, what did this have to do with anything? What else did we need to cover in this chapter? So we did the Pauli exclusion principle. Okay, so now you have to excite. What does it mean to excite something? Well, so let's take a look at this drawing pad again, and let's say that we have, let's go back to our square well because it's a little bit easier of a conceptual model to have. So I have a jump rope tied between here, and I'm swinging that jump rope up and down, and I get this one loop. If I wiggle it faster, so if I add energy to that jump rope, I can get it to jump up to one of these other states, either like this one here, or maybe this one here that has lots more bumps in it. So I can get the string to be excited, or the jump rope to be excited in these other states if I add energy to the system. But I can't go somewhere in between. I can't get the this thing to oscillate in such a way that the wave looks like this, where it's wiggling up here, because that's not allowed, because this infinite energy or infinite potential energy forbids any kinetic energy at that location, basically. And so this is not allowed. These other ones are allowed because they satisfy these conditions that are assigned, that are assigned in the problem or in the scenario. And I can jump back and forth between these two, but nowhere in between. I can only go between allowed states. So when I add energy to a system, if I can't add enough energy to the system to jump up to here, then it's just going to sit there and oscillate like this, or maybe oscillate in some superposition of all of these things, but it's not going to jump to a pure state. Once I get the right amount of energy in the system, then boom, it will. I will all of a sudden get this behavior. That will be the one that resonates with the energy that I'm adding to the system, and so it will jump up there. If I slow it down again, then it will come back down into the ground state. And so the same thing is true with these atomic orbitals. You have an electron. The electron has a probability wave. It acts like a wave equation, or it satisfies a wave equation. The Schrodinger equation is the equation that it satisfies. And the electron can exist in one of those states, or it can jump up to another state. And it can jump up to another state of a different angular momentum, right? And so it would jump from this ground state up to this first excited state. And in doing so, it now has more energy than it had initially. It had to absorb some energy in order to make that transition. Well, how does an electron absorb energy? What kind of energy can an electron absorb? Well, let's think about this. What does the electron couple to? What are the forces? If it's going to absorb energy, it has to absorb energy from some potential, from one of the sources of energy that the universe has available to us. Well, there's only 4 of those. You can have gravity. We can have gravity. That looks like gravity. You can have E&M. You can have the strong force, strong, and you can have the weak force, weak. Okay, the weak force is very, 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 very short range, and so it doesn't make it out of the nucleus. So the weak force is, you can get some interactions with the weak force, but they're extremely rare interactions with the weak nuclear force with these electrons. And so it's like 1 out of every bazillion, zillion, zillion. Okay, so this is not something that's going to cause a lot of excitations. The strong nuclear force, the electrons don't couple to the strong nuclear force. So the strong nuclear force can't provide any excitations to the energy of these electrons, not directly. You can have an atom sitting there interact with the nucleus, shift the nucleus, which then bumps all of these things up to a higher energy. But that's not a direct interaction with the electrons. Gravity, you could have the electrons coupled to the graviton, but gravity's very, very, very weak. It's way weaker than the electromagnetic force, especially on these scales. So gravity, you're not going to get a gravitational radiation, a graviton coming through and causing an excitation, even though it does couple to gravity, but it couples very, very weakly to gravity. That leaves you with the electromagnetic force. The electromagnetic force is the only force that has a realistic probability of exciting the location of where these electrons are living in the allowed homes in its neighborhood, right? So these are the allowed homes for the electron. It can live in any one of these things as long as there isn't something already occupying the quantum state. It can live in any one of these homes, but in order to transition around, you have to supply energy to do that. And so that energy has to come from one of the forces. We've excluded gravity is too weak. The weak force is too short range and also really weak. The strong force, it doesn't even couple to the strong force, so that's not a possibility. And that leaves you with the electromagnetic force. The electromagnetic force is the only viable way. Well, I guess we haven't said why this wouldn't work. But the electromagnetic force couples to the charge on the electron, and it's a very strong coupling. The electromagnetic force is certainly relative to the other forces is quite strong. The strong nuclear force doesn't count because it's got 0 coupling to that. So the electromagnetic force is the force that can be absorbed, or energy from the electromagnetic field is the energy that can be absorbed by these electrons and cause them to jump around into these different states. So that is the electromagnetic force. And that's why when you have, here's your atom, okay, here's my atom, and I've got these different energy levels that are available to me but not occupied. Here's my electron. If I want this electron to jump to another energy level, it's going to do it by absorbing a photon. So you have a coupling to the electromagnetic field. There's a disturbance in the force. The electromagnetic field comes towards it. It deposits enough energy into the system to bump the electron from one of these energy levels up to another. So thank you, King's Throne, for that. 4 years. 4 years of subscriptions. I appreciate that. So that is what that's how it comes up here. When it jumps back down, it's giving up that energy again, and it's going to give it up to the force that's most readily available to it, which is the electromagnetic force. So photons will be emitted when it jumps down an electron and an energy level. It will be absorbed when it jumps, and that absorption caused it to jump up an electron. If you had a different force, if there was another force that they coupled to, say like the spintronics force, or the space chicken force, okay, or the cactus cooler force. So if you have a force like this and it can couple to this force, then it could emit and absorb radiation from that force. But it's only the electromagnetic force that has a realistic probability of doing this. So like I said, you could imagine doing this with the weak force, that like a neutrino out of every bazillion comes in and the W emits some W and couples to this, and then somehow you couple it to the nucleus as well, because, or you get, you know, what kind of diagram would it take? Let's think about this. What kind of diagram would you have? Let's say you have a Z. So you have a Z particle here. You could have an electron and a neutrino coming in. So a neutrino could come in, hit the electron, interact with it, and then it cause an excited state. So you could get some interaction with this, but you're talking a coupling of a neutrino to the electron, which is really, really weak. So thank you for that sub. I appreciate that as well. All right, so that is the 2 subs. Appreciate both of those. So that is the situation. And that's why the electromagnetic force is what is the thing that causes electrons to jump up and down between the different energy levels. And so they'll absorb a photon or they'll emit a photon, and that's related to the location of these energy levels. Now, how much energy is associated with each of those energy levels depends upon the number of charges in the nucleus, the number of electrons that are going around it, and so forth. And so each individual element will have its own set of energy levels that it can bounce, that the electrons can bounce around in, and therefore it will have its own set of energies, allowed energies, that correspond to those transitions. So, but that's not all. There are other structures or other... okay, so let me do this. Here is your nucleus. Here is your ground state shell for, like, let's pretend this is helium nucleus or something like that. The ground state shell that you have. Okay. You can have 2 electrons in it, one that spin up and one that spin down. They don't necessarily have to be on opposite sides of this. They could be right next to each other. There's some probability wave associated with them. They both have the same probability of being at any location. The difference is that they have 2 different spins. Okay. Let's see, here's a question. Can the electron change its nature with enough energy? It can't change its nature because that would violate the quantum numbers. The quantum numbers associated with the electron are all conserved. As far as we can tell, they're conserved. So that's the lepton number, its electric charge, its spin. These are all conserved quantities. And so in order to change the nature of the electron, I would interpret that as saying, can you change the quantum numbers of the electron? You can flip the spins of the electron over, for example, but you can't change the value that the spin has, like the absolute value that the spin has. So you can have plus 1/2 spin or minus 1/2 spin, but you can't have it at plus 2 spin or something like that. So this is, so these are the 2 electrons that can fit in this shell, but these both have the same energy, right? They both, if I come back to this figure, they both are in this shell. They have the same energy quantum number. Right, here's the energy quantum number right here. They have the same energy quantum number. So how can you tell them apart? Well, you can't really tell them apart in terms of, like, if you're just measuring the energy of the electron in an atom, then these are identical. They have the same spin, or I'm sorry, they have the same energy. However, what you can do is add a perturbation. You can add some other field or change something about the ambient field that will cause this one to behave slightly differently than this one. It will add some energy to one and take away some energy from the other. So, for example, what you can do is I have my atom right here, and I'm going to put it in some ambient electric field or an ambient magnetic field. Let's do a magnetic field. So I'm going to have an ambient magnetic field. So here is my ambient magnetic field. It's going to be pointing in this direction. So now if I have an electron here, here's my electron. If the electron is spinning this way, so the spin of the electron, when I say the spin of the electron is pointing in a given direction, I'm saying that your right thumb is pointed in that direction. The spin corresponds to the direction that your fingers curl, because we always use the right hand rule, because left-handers have they get too much ink on their hands when they're writing, and so they don't get to have the convention be in favor of them. And so you have the right-hand rule determines which direction the electron spins. And so the electron is therefore going to be coupling, because now you have kind of a spinning charge, even though it's not really spin. You have a magnetic field associated with that, and that magnetic field is going to try to align with the ambient magnetic field. And so this thing will have a different energy level than an electron that's spinning in the opposite direction. So this has its electron, like its magnetic moment, aligned with the magnetic field, and this one has the magnetic moment anti-aligned with the magnetic field. And so that's going to cause, even though in principle they have the same energy, you've added an ambient field, some perturbation to that field that's going to split these two spin states from each other. It will add energy to one of the states and subtract it from the other state. So it's a way of breaking this energy, the degeneracy between the two. So they would nominally have the same energy. Now you've broken that symmetry, added energy to one and taken it away from the other. And so what will happen is you'll have photons that correspond to different energy transitions, but going from this shell to this shell with the spin oriented this way is a different energy than going from this shell to this shell with the spin oriented that way. And so you get two different energies associated with that. You get two different colored photons associated with that. And this is called the Zmon effect. Zmon effect. So that says Zmon. Let me show you what it looks like. Zmon effect. Okay, so there's a question here. What about phonon interactions like with Raman? So I'll talk about Raman spectroscopy in a minute. Don't let me forget that. We'll come back and talk about Raman spectroscopy. 21 centimeter hydrogen line is an example of directional spin change. Yes. So the 21 centimeter hydrogen line, it's 21 centimeters, not 51, but it's 51 centimeters if it's redshifted by redshift 2.5. So redshift 2.5, then you're talking about 51 centimeter. So the Zmon effect, if we look at one of these spectral lines, that is not it. That's also not what I'm looking for. Well, this kind of shows you what I was saying. As you increase the magnetic field, then the separation between these energy states increases. I want just to see the actual Zmon effect. And this is not helping. I want a picture of the Zmon effect. I want a good picture of the Zmon effect. So this is what I just described. So you have one where, you can, none of these are pictures. Okay, here's a picture. So these are the Zmon splitting that you get. The one in the center is if you have a spin that's not aligned, or it's neither aligned nor anti-aligned with the magnetic field, then you get no effect. If you had, so suppose you're in a shell where you have 5 different projections. So here's your z-axis, and you've got this one, you've got this one, you've got no projection, you've got that one, and you've got this one. So this is the 5 different allowable projections from, say, one of these higher order electron orbitals, so higher angular momentum electron orbitals. Then when you put it in a magnetic field, you're going to get 5 lines. It's going to split into all possible couplings. And so you're going to get something like this. So here are all the different lines that can appear from these different things. And it shows up in the spectrum of light that gets absorbed by the atom or emitted by the atom. So that's the Zmon effect. There are other things that you can do that give you like hyperfine transitions. So this is the fine structure. The fine structure tells you when you have a magnetic field how much the lines split. Gives you the fine structure of the atom. It tells you how the electron spins are arranged within the atom. And then there's a hyperfine structure. I don't remember exactly how the hyperfine structure works. Is it like some coupling to the nucleus? Anyways, I should look that one up at some point. Thank you for that sub. Let's see. I'm trying to visualize an atom. I've always wondered, does an atom have a rotation-like position, or is it meaningless to talk about since they're not really solid things? So an atom is a collection of quantum particles that all, it's a collection of quantum particles that are all interacting with each other through the various forces at their disposal. So you have the nucleons in the center that are interacting by the electromagnetic force and the strong nuclear force and the weak nuclear force, although the weak nuclear force is much, much weaker than everything else, so we can pretend to ignore it for the moment. So these all interact with the strong nuclear force and the electromagnetic force. The strong nuclear force is dominating while the nucleus is small. As the nucleus gets bigger by adding more stuff to it, then the electromagnetic force becomes increasingly strong, and its relationship to the weak nuclear force is what allows the nuclei to break apart when they get too floppy. But for small nuclei, it's the strong nuclear force that dominates, holding it together, although the electromagnetic force is present. For the electrons, since they don't couple to the strong nuclear force, they don't bind to the nucleus. There's no coupling between the electron and the nucleus. Instead, this interaction here is the relationship between the electromagnetic force produced by the nucleus and its effect on the orbiting or on the electrons that's in the vicinity. They don't orbit. Electrons don't fly around. Electrons exist. There's some probability of measuring them in a given location. That probability is given by the solutions to the wave equation. And in particular, it's the steady state solutions to the wave equation, Schrodinger's wave equation. Okay, so this is a structure built by the strong nuclear force. This is a structure built by the electromagnetic force. If gravity was a lot stronger, then you could imagine another structure, like similar structures corresponding to gravity. You could have a gravitational coupling between, you could imagine having some other particle going around here that has a coupling to gravity. But gravity is just weak on these scales compared to the other forces involved. But you could imagine a different force like the rebel force from Luke Skywalker or from UNLV. So the Luke Skywalker force, the midichlorian force, if you have a particle like a Yoda particle that has a lot of midichlorians and has a strong midichlorian coupling to these things, then you could get quantum states associated with the Yoda force. And the Yoda force with these midichlorians, it doesn't necessarily, so we'll call it the Yoda Force instead of the Rebel Force. I think it sounds better, Yoda Force. Kind of rolls off the tongue a little better. So if we had a Yoda Force, and that Yoda Force could be like 1 over r squared, right? The potential could be something else. It doesn't have to be 1 over r like this, or this Yukawa field. It could be a Yukawa field, so it could look like either minus lambda m, something like this. So you have a Yoda Force. It's got some new couplings associated with it. Maybe it depends upon distance in a different way because we live in a multidimensional universe. So the Yoda Force, if you had particles that couple to the Yoda Force and the particles in the nucleus couple to the Yoda Force, then you could get a whole new chemistry-like thing. We won't call it chemistry because nobody likes chemistry, but you could get a whole new branch of science that corresponds to this Yoda Force and how the Yoda Force couples the Yoda-coupled particles to the nucleus, assuming the nucleus couples to the Yoda Force, and how these things interact with each other. So you could have a completely parallel set of chemistry, like effectively the equivalent of a chemistry for this other force, just like nuclear physics is essentially another form of chemistry. Like chemistry is how do these electrons interact with each other given the fact that they satisfy Schrodinger's equation and they couple with the electromagnetic force. The nucleus is exactly the same proposition. Here are a set of particles that couple to each other via the nuclear force. What are the different structures that you get and how do they arrange themselves? That's nuclear physics. It's just like chemistry, except it's with nucleons and the strong nuclear force instead of with electrons and the electromagnetic force. So if you had a Yoda force, then you would get a new branch of science, and of course it'd be a branch of physics because we are the best, a new branch of physics with its own set of interactions, and you could make your own set of complex structures like nucleus for the nuclear forces or chemical elements or chemical molecules for the electromagnetic force. Now you have a whole new chemistry-like thing with the Yoda Force. So there we go. That's that's what you would get if you had something like that. All right, let's see. There's a question in here. What does it mean by finding an electron? Well, when you find an electron, when you locate an electron, you can make a measurement to say this is the location of this electron. There are ways to say what energy does this electron have by looking at how it bounces around, or what energy did this electron have as it went from one place to another. So something like that. Thank you for that raid, Skylius, with a raid 313 people. Wow. So thanks for that raid, Skylius. I appreciate that very much. So we are talking about the electromagnetic force. So let's go back and review what I briefly introduced here with the electromagnetic force, or with electrons, and how this relates to chemistry. So the question that came up earlier was, how do what are these atoms? How do we know what an atom is? How do you make such a thing? And the description that I came through with was that an atom is a collection of particles that are all interacting with each other with various forces. And there are two forces in particular that matter the most. Two forces that matter the most are the electromagnetic force and the strong nuclear force. But they're not the only forces that are there. So what you do is you say, okay, these have different strengths. I have a bunch of particles. Some of these particles interact with the strong force and the electromagnetic force. Some of the particles interact with only the strong force, and some of the particles only interact with the electromagnetic force and not the strong force. So what's going to happen? Well, the ones that are interacting with the strongest force are going to be most tightly bound. The strongest force is going to pull them together into really tightly bound objects. So I'm going to take these things, I throw them into the box. The ones that are most tightly bound are going to sink to the middle, and they're going to be stuck together through the strongest of the two forces. Turns out that the strongest of the two forces is the strong nuclear force. So now you have a whole bunch of particles that interact with the strong force in the center because that's this force, that's the strong force. That's why they called it that. But it didn't need to be called the strong force. It could have been called something else. And so you get a structure that forms from the solution to Schrodinger's equation as it relates to how do these particles interact via the strong force, what are the allowed energy levels, how do those energy levels relate to each other. So you can build up the nucleus. Now you have another set of objects that interact with the electromagnetic force but don't interact with the strong force. The electromagnetic force is weaker, and so you're going to get larger objects that form because they're more loosely bound. And so that's where the electrons come in. So the electrons are going to be out here as they interact with the protons, because it's only the protons that couple to the electromagnetic force in the nucleus. So the protons are bound together with the neutrons because of their coupling to the strong nuclear force. The electrons are bound to the atoms because of the coupling between the protons, which happen to have an electric charge. They didn't have to, but they do. And the electrons that also couple to that electromagnetic charge. And it's a weaker force, and so you get floppier, bigger, and flimsier objects. And so then what you missed, we had just wrapped it up, but we're going to bring it back in right now, is that if we invented a new force, and we called it the Yoda Force. So the Yoda Force is a new force that, let's say that the Yoda Force is weaker than the strong force, but stronger than the electromagnetic force, and that it couples to different particles that are in here. So now you're going to introduce a new set of allowable states by particles that couple to this new force. Maybe the neutrons have the Yoda force, but the protons don't. And so now you have a set of particles that can couple to these objects. That the reason that they couple to these objects is because the strong force is there and sets up the kernel from which you can build your structure. The neutrons, in this case, this pretend mode is that the neutrons will source this Yoda force. And we have another particle out here. What should we call them? We'll call them Skywalker particles. So this says Skywalker. So you have Skywalker particles that couple to the Yoda force through the neutrons. And so it will build up their own quantum states, their own set of locations where they can live and the energies associated with those locations. And this Yoda force, can have a variety of different forms. It doesn't have to follow the 1 over r squared or 1 over r potential that the electromagnetic force does. It doesn't have to have the Yukawa potential that the strong nuclear force does. It can have, whatever it is. It happens to, if these exist in a 9-dimensional hyperuniverse, then it could have a 1 over r to the 8 potential instead of a 1 over r squared or 1 over r potential. So that would be a 10-dimensional hyperspace. But anyways, you get the point. That it doesn't have to depend on the distances the same way that the other forces do. And so it's going to get its own set of quantum states, and it's going to have its own structures that it forms, and therefore it's going to have the equivalent of chemistry, except with the Yoda force. So now you're going to have the electromagnetic chemistry that gives us all the wonderful things that we eat and that we, like wash our faces with. And then you're going to have the nuclear the equivalent chemistry that's nuclear physics, so the structure of the nucleus, and you would have this new branch of effectively chemistry associated with the Yoda force and the quantum states that are allowed and how those quantum states couple to each other. So that is, that's why atoms are made the way that they are, is because you have these two different forces, you have a bunch of particles that couple to those forces, and the strength of that coupling determines the size of the structure that you form. And then the fact that they have to satisfy the Schrodinger equation tells you what are the allowed states that they can occupy while they're in that structure. Okay, so coming down to here. Do we know what the strong force is, like a gravity type force or unknown? We do know what the strong force is. The strong force is related to scam likely. Strong force is related to scam likely. The strong force is related to a type of symmetry that you need to have in the Hamiltonian in order to preserve some quantum numbers. But the moral of the story is that you have some subatomic particles, they're called quarks. Here's a quark. That subatomic particle has certain mathematical properties, and that mathematical okay, so let me back up a little bit. One of the things that we've talked about throughout this series is the fact that the energy that an object has, so the energy that an object has depends upon both the kinetic and the potential energy. But one of the things, so the potential energy that an object has is the energy that object has. That's an ugly P, but so it's kind of a goofy looking potential energy. The potential energy that an object has depends upon its location. So this is energy from position. Okay, and that depends upon our coordinate system that we attach to the universe. So like I look out at the universe, I'm going to attach a coordinate system, and then I'm going to say, I'm going to measure my potential energy with respect to that coordinate system. I'm going to measure my kinetic energy with respect to that coordinate system. Because if I'm moving along with an object, then it has no energy from my perspective. If I have a different perspective and my perspective is moving with respect to that object, then I assign that object energy. The same thing's true with potential energy. I have an origin, I measure the energy that it has because of its configuration relative to that origin. The energy that it has because of its configuration is because of the presence of, so here's my object, the presence of this ambient, so here's a gravitational field, this might be an electromagnetic field. And so it's going to have potential energy in how it couples to the ambient fields that are available to it. Okay, now, because I can because this all depends upon my coordinate system, you can imagine the following thing. Suppose that I have, and this is an analogy that I'm stealing from someone else. Suppose I have a mountain range here. So, and I have an airplane that's flying up like this. So this is an airplane flying in this direction. Okay. And I measure the energy, the potential energy relative to the ground. Okay. But the ground keeps evolving under my feet, right? It's not sea level necessarily that I'm measuring. I could measure it with respect to sea level, or I could measure it with respect to the ground. And so as the airplane is moving along, if I measure it with respect to the ground, then the potential energy of the airplane is changing all the time. As it's moving along, the potential energy of this airplane is changing as it goes across here. And so, but the energy is not really changing. It's only like changing because my definition of what potential energy means forces it to change as this separation changes. So what you have is the way that you correct for this, the way that you say it's not really changing, but it's kind of changing, is that you have it coupled to you introduce to the system a force or a field that forces this thing to change its energy as it moves along. So you say, okay, instead of this thing having constant energy as it moves across, the energy is actually changing because of the effect of the background. And so the only way for the energy for some object's energy to change is if I exert some kind of force on it. That's the only way that I can get the energy to change. So what force am I going to add? Well, I'm going to invent a force that will cause this thing to transition, its potential energy to change from one place to another. That kind of force is called a gauge force. Okay? A gauge particle is something, it's like a force that now I'm here, and when I move a little bit to a different location, then I have to exert this force on it to correspond to that change in potential energy. So that's a gauge force. So the electromagnetic field is basically this kind of gauge force. So if you have a single particle that's moving along, the electromagnetic field is one of the ways that you can change the energy of that particle given a coordinate system. So what was the question again? So now that I went off on that tangent, I should come back to this and say, do we know what the strong force is? So the strong force is another one of these gauge forces that corresponds to a type of potential energy that one might want to have. So how does it manifest? the strong force is, so there's a book, I don't have the book because I checked it out from the library when I read it, but the book is called Deep Down Things. And it is my favorite book, my favorite science book that I've ever read, actually. Deep Down Things, Quantum. It's this book right here, The Breathtaking Beauty of Particle Physics. So this is my favorite popular science book that I've ever read, is Deep Down Things. And it goes into detail about like what are the symmetries, like what are the things that we want our mathematical structures to have that force us to have a strong nuclear force. So I don't remember the details now because I read it like 20 years ago. So anyways, the strong nuclear force is the particle, the gauge particle that's exchanged between any two other particles, so a quark. Quarks interact with the strong nuclear force. So quarks, they can emit or absorb gluons in the same way that charged particles can emit or absorb photons, electromagnetic fluctuations in the electromagnetic field. This is fluctuations in the strong nuclear field, or the quark field, or I'm sorry, the gluon field, and that couples these quarks together. So that's the strong nuclear force. The properties of the strong nuclear force are related to mathematical symmetries that I can't remember because I haven't looked at it for a long time. Okay, so let's go. There's some other questions here. So gravity is a little bit weird. We can't really say that it's like gravity because we don't really understand the fundamentals of gravity. We understand classically how gravity operates. We understand general relativity, but we don't understand how quantum gravity works. Okay, it's probably hard technical, but since the nuclear force is so much stronger than the gravitational force, why does a black hole which gravity overcome the atoms and destroy them? That's a great question. The great question that we have before us is, if the strong nuclear force is stronger than gravity, then why does gravity win in the end? The reason is, and it's a good reason, the reason is that with, let's take the electromagnetic force as an example, and then we'll do the same example with the strong nuclear force. The electromagnetic force comes in two varieties, or sorry, the coupling that you can have to the electromagnetic force comes in two varieties. We call it positive and negative. We didn't have to call it positive and negative. We could have called it black and white. We could have called it green and red. We could have called it whatever. But we assigned two different quantities to it. A and B, could have been A and B. These are the two different forms of coupling that you can have to the electromagnetic field. When the electromagnetic field gets too strong, then you can actually produce, so you have too strong of an electromagnetic field, so you have a super high energy photons bouncing around. This thing can spontaneously produce positive and negative particles out of the vacuum. And so you are rarely going to have a situation where you can build up a significant amount of one charge without having the other charge nearby. They will tend to group together. So while you might have a charged particle, like here's your charged particle that's drifting all by itself in space, it will eventually capture another particle nearby, and then you get this pair that are coupled together. They're coupled together because that's the nature of the electromagnetic force. It takes like charges and it brings them together and couples them together. So now, from a distance, this thing looks neutral. If you get deep into it, then you can recognize, oh, there's a bunch of positive charge in the center and there's some negative charge on the outside. So you can tell that the atom has structure if you look at it at very short distances. Like once you probe deep into the middle of it, you can tell, oh, the negative stuff is on the outside, the positive stuff's on the inside, and that the charges are actually separated. But from a distance, when you're looking at large distances or looking at it from a long ways away, it looks like a neutral object. It's just, it's there. The negative charges balance out the positive charges. So you don't build up a whole bunch of positive charges without eventually getting a bunch of negative charges around it, which then cancel out those positive charges. So that's, with the strong force, you get the same thing. The strong force, you have three different charges associated with it. So instead of having just this positive and negative charges, you've got red, green, and blue. They call them color charges. So you've got three charges, green and blue, and you can only mix these things together in combinations that are color neutral. So you can only mix them together in red, green, and blue triplets, or you can mix them in like red, anti-red. So each one kind of has a negative version of itself as well. So I guess the true thing that's going on here is that with the electromagnetic force, you've got the electric charge, and that electric charge has a sign of positive or negative. Here you have the color charge with three components, and it can have a positive and a negative of each of those three components. Maybe that's a more appropriate way to envision this. Okay, but you can have red, anti-red, you can have green, anti-green. You can have superpositions of these colors, but that's a thing for another time. So you can only have color neutral combinations of these things. You can have like red, green, blue, blue, anti-blue, something like this. Okay, so this is called a hadron. If you mix them together this way, we're getting a little bit ahead of ourselves because I'll cover this in a couple days as well in more detail, or in similar level of detail. So you can have these triplets that are called hadrons, where you get a red, green, and a blue together. You can have these pairs where it's a color and an anti-color. These are called mesons. And then you can have these ones here. This is a pentaquark, because there's 5 quarks, but it's still color neutral. You have red, green, and blue, and then you have blue and anti-blue. Okay, so a pentaquark, these are all color neutral. You can't have bare color charge. The universe won't allow you to have a bare color charge. And part of the reason for that is that the gluons themselves also carry the charge. It would be like a photon also carrying electric charge. So if you tried to isolate, say you have a red, green, and blue combination, and you tried to take this blue thing and pull it away, what would eventually happen is you would build up so much strength in the color field, in this gluon field, that it would spontaneously produce, it would spontaneously produce this. And so you'd spontaneously produce this meson with blue, anti-blue. The blue would attach to this collection and give you the particle that you had to begin with, and the anti-blue would attach to this one that you're trying to pull away. And so you get a red, green, blue hadron plus a blue, anti-blue, blue, anti-blue meson. So this would be like a pi, or something like that, a pion or a kaon or whatever. So that would be, this is what happens if you try to pull a nucleus apart. It will spontaneously produce the energy generated in the gluon field becomes large enough to allow E equals mc squared to come in and produce a particle-antiparticle pair. The particle will go with the hadron, the antiparticle will go with the quark that you're trying to extract, and you end up with a hadron left over, like a proton, plus a bunch of debris that comes out. Okay, so I don't know if that actually answered the question, but it was a good tangent to go on. So the question was, why does gravity win in the end? And here's the reason. So all these other forces, the strong nuclear force, the weak nuclear force, the electromagnetic force, they come in combinations that are neutral. Or if you build up too much in one area, then it will pull other stuff around it and ultimately become neutral to that force. Gravity doesn't work that way. Gravity is always additive. So there's no anti-gravity. You can't have a massive object and an anti-massive object. You can have antimatter, but antimatter has regular mass. So there's no anti-mass. So this thing doesn't exist. And so you always add the mass, this mass, this mass, you add all these things together, and it always is a positive and always creates this attractive force. And as a consequence, even though it's the weakest of the forces, it's the only one that doesn't cancel itself out over time, like once it comes into equilibrium. And so you keep adding stuff to it, and eventually even small amounts of substance are going to produce a large effect in the end. And so gravity is going to win because there's no anti-mass, there's no negative mass. And eventually it is strong enough to overcome any other of the forces, simply because you add enough stuff to it. Okay, let's see. Most likely gravity has more than one component. Even the Higgs boson, we only have a partial view. We haven't done anything new, only thought about building yet a large hadron collider to look for dark matter. So it is possible that gravity has more than one component. That is true. The graviton, the way that we envision it, it's a spin 2 particle. And you could imagine that the gravity is part of actually a larger structure that has different particles with different spin properties. You could have a scalar particle and a vector particle. So a photon is a vector particle. You could have a scalar particle like the Higgs that's related to the gravitational force. So far there's no evidence for that, but there's also no evidence to refute it. There's nothing that says that it doesn't work that way. Figuring out electroweak force was groundbreaking. We needed something like that breakthrough with gravitation, and for quantum stuff, maybe dark energy, dark matter, even if it even exists. So I believe that dark matter does exist. I'm not on board necessarily with Sabine on this one. But there's, I'm fine with Mond as well. It could be real, but they have some questions that need to be answered, especially questions related to the torsion pendulum experiments, in my humble opinion. Okay, so speaking of books, what do you think about Sakurai versus Griffiths? Well, Griffiths is an undergraduate textbook. Sakurai is a graduate textbook. So if you want to understand the essential elements of it, then Griffiths. If you want to do more technical problems, then Sakurai. Flatlanders invent a force to explain a 3D surface effects they can't perceive. That's right. We are all Flatlanders. And Demon Machine raids as well. So that's 2 raids. Wow. Okay. Okay, great explanation. Gravity can never cancel out, only adds up and gets bigger. Yes. Can gravity be neutral? Can gravity, only if there's no energy associated with it, because it's actually, gravity couples to energy. It doesn't couple to mass. So in low energy environments, mass is most of the energy, right? So this is something we covered not long ago, is that the energy of an object is the sum of its mass energy plus its momentum. And so in a low energy environment where the momentum is small, then E equals M, right? And then you have C squared in there to make the units come out right. So energy and mass are equivalent in the low energy environment. In a high energy environment, like a photon, photons also couple to gravity, otherwise they wouldn't deflect. And so when you have a high energy environment where you have to add the momentum in there, then it's actually the energy that couples to gravity, not the mass. So can gravity be neutral? Only if you have a massless, energyless particle. Let's see, I'm assuming it's because gravity doesn't have polarity like matter. Yeah, so exactly, Geek Boy, what you said. Is gravity considered weak in comparison to the strong force because we only experiment using Earth's gravity? Gravity is weak because of the strength of the coupling that it has. So if you look, the way that this works is, for example, the force between, or the energy between the electromagnetic force is, the energy is going to be, what is it? It's KQQ over R. And so this constant out front, that K, is 9 times 10 to the 9. It's 1 over 4 pi epsilon naught, if you want to write it that way. So this is the coupling of 2 elemental charges, is that strength. For gravity, the energy of gravity, so this is E and M, this is for gravity, it's going to be Gmm over R squared. And so this G is 6 times 10 to the minus 11. And so it's 20 orders of magnitude weaker. And that's with a kilogram of coupling. If you take the proton as the fundamental unit, so this is taking a kilogram as a fundamental unit, and I guess a coulomb as this, but if you say, okay, I'm going to take the electron or the proton as the fundamental unit, and you put the proton mass in here and the proton charge up here, then this ratio gets even worse. For the weak force, let's do the strong force. For the strong force, E strong, you're going to get some number. I don't know what it is. We'll call it theta for lack of a better thing. And then you're going to have the color charge. I guess we'll call it QQ. And then it's something like, oh, I'm sorry, this isn't R squared. This should be just R, because that's the energy. And it's E to the minus the mass times the distance divided by the distance. So it's a Yukawa potential. I haven't gone through this derivation for decades, so I don't remember exactly what this thing looks like. But you're going to have a coupling out front, and that coupling is going to be larger than this coupling to the electromagnetic field. So that's what they mean by it's weaker than gravity. It's that if you take kind of an elemental particle and then you plug in the numbers, the constant out front, the ratio of these fundamental constants out front is going to be the thing that determines their relative strength. So the one that's used most common is the proton. The proton is the particle that couples to all of these forces. Are there any particles that are there any other particles that couple to all 3 of these forces? I think the answer is no. Proton is the only stable particle that couples to the strong force, the weak force, the gravitational force, and the electromagnetic force. So that's probably why they use it, because that's the thing to compare to. Okay, let's see. Dark matter doesn't affect the space-time plane in a way similar to negative mass. No, so dark matter is also attractive. Dark matter is attractive. Dark energy appears to be repulsive, but it's not clear where that repulsion comes from or what's causing it. It's not clear what the microscopic properties are for dark energy that cause this to happen. Now, in a couple sessions, I think it's maybe the end of next week or maybe the week after, we'll be doing the unit on, like the chapter on dark energy and cosmology and stuff. Let's see. So the range of all these forces, I wrote it wrong. If the charge carrier, or if the force carrying particle, so if the photon had mass, then it would also have a form that looks like this, where you have the mass here. This is the mass of the particle that does the exchange. So in this formulation, it's the pion, it's the mass of the pion that they're talking about. So it's the force exchange between two nucleons. And it's through that process that I showed you earlier, as you pull a quark from one place and try to move it to another, it will spontaneously produce a quark-antiquark pair. That quark-antiquark pair is a pion. The lowest energy state is a pion, and that's what will shift back and forth between the nucleons in the nucleus. And so this M here is the mass of the pion. The Earth is not equal to, the Earth is not flat, and you can tell this by doing measurements of the position of the stars in the sky as you walk north in latitude. Is it correct after thinking about it? Since the photon has no mass, it has no momentum. Okay, so Puzzle Gamer, I did talk about this not long ago. The photon does have momentum. So we normally think about momentum, P is equal to mv, but that's actually not what's going on. The momentum is related to the energy, like this. And so this says that the energy is the sum of the mass plus the momentum. And so if you have a massless particle, then the energy and the momentum are equal to each other. It forces you to travel at the speed of light. If you have no mass, then you move at the speed of light. And so your energy, if converting this to regular units, you get energy as PC. So the momentum of a photon is equal to the energy divided by the speed of light. Since we know the momentum exactly, the position of the photon ever can't be located. Yeah, so there, it does have a momentum, and it's defined in these terms. This formulation of momentum, this one here, is a low energy limit. It's what do you get when you use this equation for a low energy situation. So I did the same thing with energy, where if you use that same formulation, E equals, that's actually what it's, so there's E squared equals M squared plus P squared. There's also equivalently that E equals gamma MC squared, where gamma is the speed of light thing, and this C here should be in here. It's like M squared C to the fourth PC squared. This gamma right here is 1 over the square root of 1 minus V squared over C squared. And if you do the Taylor expansion, you end up with something that looks like this. Energy is equal to mc squared plus 1/2 m. The c squareds cancel, and you get a 1/2 mv squared. It might be v squared over c squared. But I don't think so. I think it looks like this. I'd have to go through the derivation again to do it. But anyways, you get a Taylor expansion of this for low velocity. You get this, and then you just say, because energy depends on the coordinate system, then you can basically just drop that one out, and then here's your kinetic energy that you have left over. What about the W bosons? W bosons are for the weak nuclear force, and so it has the same, it's just like a photon, except it's got mass as well. By the way, I would talk about Raman scattering. Yes, very good. Oh, okay, so back to what we were at the beginning of the stream, and that is, what is Raman scattering? So suppose you have a crystal. Here is your crystal. The crystal is composed of a whole bunch of individual atoms like this. So here are the individual atoms. Or another way to say this is that the crystal comprises all these atoms. It is not comprised of all these atoms. Make sure that you don't make that mistake. Okay, the crystal contains the atoms. The crystal comprises the atoms. So here are the atoms in this crystal. When you have any kind of solid structure, it's able to support phonons. So you can get sound waves that bounce back and forth within this crystal. So the sound waves, like any other quantum system, have a tower of available states to them, different types of oscillation modes that they have available. Each one of those oscillation modes is going to have its own set of standing waves that you can get, its own set of quantum states. Okay, so what's going to happen with Raman scattering? You have this crystal, it's got sound waves bouncing around. Those sound waves have some kind of energy associated with them. Or it's got sound waves that are available to it. It can excite into different sound waves. It's not necessarily bouncing around. The sound waves aren't necessarily there, but they could be there if they were excited properly. It's like saying I have a baseball bat and I can get the baseball bat to ring if I hit the baseball bat, but I'm not going to hit the baseball bat. And so the ringing state is available to me, but I haven't yet provided the energy that it takes to populate that ringing state. Okay, so here's my crystal structure. What I'm going to do is I'm going to shine a laser beam. I'm going to shine a light in like this. So I have a photon coming in. So here's my photon, and so I'll add a wavelength to it here. So here's my photon coming in, and I'm going to hit this thing and bounce off of this crystal. Okay, but the photon that's coming in is going to couple to this crystal in such a way that it's able to excite an oscillation of this crystal. So now the crystal is going to start oscillating. So here is the picture of an oscillating crystal. Okay, so here's this oscillation. Here's all of the things in here. Okay, so that oscillation takes energy out of the original photon. So the original photon comes in, let's say that it comes in green. Okay, it bounces off this thing, comes up like this, but now it's lost some of its energy, so it's going to bounce away red. And so the question is, here's the incoming light, here's the outgoing light. What is the difference in energy between the outgoing red photon and the incoming green photon? That difference in energy must have been absorbed, because energy is conserved, must have been absorbed by by the system, by this crystal, and it therefore excites at that frequency. So what you do is you shine this light in and you look at what are the colors that come out. Okay, what are the photons that come out of the crystal? And the variety of photons that come out of the crystal tell you how many different, what are the different excited states that you have in this crystal structure. So let's take a look at a Raman spectrum. Raman Spectrum. So what you can do is you can use the outgoing energy of the photons as a way to diagnose what is the crystal structure that you form. So here's an example of a Raman spectrum. Well, okay, so it's a low resolution example of a Raman spectrum. So here's the intensity, and here's all these different wavelengths. It's the Raman shift in inverse centimeters, which is some unit that people that do this stuff use. But these correspond to different wavelengths of light, different wavelength differences between what you put in and what you get out. So each one of these corresponds to a different vibration mode of that crystal. It can shake this way, it can shake this way, it can shake this way, it can, there's a variety of different ways that it can shake. Not only can it shake like that, but it can also shake, not only can it shake so that it's oscillating like this, but it can also oscillate like this, right? So you can get this kind of oscillation, you can get this oscillation that has more, you can get this oscillation that has less. So all of these are available to it. And so as you have these photons bouncing off of it, you're exciting these different states. And the ratios that you excite them are given by the heights of these different peaks. And so the ratios that you excite them also tells you kind of what the gap is between the energies, although you can read it directly off of this spectrum. So that's what Raman spectroscopy is you shine in light of one color, and color corresponds to energy. So light comes in with a given energy, it leaves with a different energy. That energy is absorbed by the vibration modes of the crystal, and it tells you about the structure of the crystal. You can also have another effect that takes place, and that is, here's your crystal. It's already at a high temperature, so it's already shaking. High temperature means there's lots of vibrations going around, so it's already shaking. And then you can send in a green photon like this, have it bounce off, and it comes off blue. So green going in, blue coming out. And that implies that it actually picked up energy from the crystal. And that also tells you about the structure of the crystal. In fact, it's a way you can measure the temperature of an object. What you can do is look at the strength of so you send a line going in, and then you have the reflection coming out. Some of the reflection coming out is going to be some blue and some red. So when you look at that Raman spectrum, you're going to get something that looks like this, where this peak is the peak that, let me draw it slightly differently. You're going to get something that looks like this. This peak is the energy that's absorbed. Like the green light comes in, hits this, absorbs some of the energy, or takes energy out of the oscillation and adds energy to the photon. And then this peak is going to be the energy coming in and then exciting oscillations in the crystal, and it gets removed from the photons. And you can use the relative heights of these things to determine what's the temperature. Which direction is the energy flowing most favorably, into the photons or being pulled from the photons. So that's kind of cool. Does the light really shift that much, several hundred nanometers? Well, it's no. So that was like me going red-green is just a way of saying here's higher energy stuff and here's lower energy stuff. It's actually usually pretty small shifts. The shifts are measured in a unit that I don't understand because I haven't worked with it. I mean, I understand that it's there. These are wave numbers, but I don't know what that means because I don't work in this discipline. So this is the size of the shift that you get. How much cooler can you make the crystal by bouncing photons on it? How much cooler can you make the crystal by bouncing photons on it? So, in other words, is it possible to cool the crystal down by having photons come in and absorb, the phonons out of the crystal? That's interesting. I don't know the answer to that question. You'd have to be pretty fancy about how you did it. You'd have to probably understand what's the phase of the surface. You know, what oscillation mode do you have and what's the phase of the oscillation mode, and then time it so that it arrives at a time when it's able to properly scatter the photon. So that I don't know. Does this apply to laser thermometers that they use nowadays to measure body temperature? So I'm not sure what the things that use body temperature, you're not actually using the laser to measure the body temperature. What you have is the laser tells you where you're pointed. So when you have one of these thermometers, you have this gun-looking thing like this. It's got a laser coming out of it, but it's actually got an infrared detector here. The laser tells you where you're pointing it, and the infrared detector is what you actually have. Here's the forehead, and the infrared detector brings in light coming directly emanating from the forehead and then measures the temperature that way. Let's see. If these lasers are strong enough, are the crystals able to generate sound, since it looks like the oscillating pattern is the same as sound wave? It is a sound wave. So these are sound waves. These are phonons oscillating. A phonon is a sound wave. So these are phonons. They are sound waves. You can amplify them. So you could put it on like a piezoelectric something. So as the thing is shaking, it's compressing a piezoelectric disc that uses a squishiness. Like when it gets squeezed, it creates an electric signal. And then you could run that electric signal to an amplifier and then amplify it and make the sound. Being able to hear it is a bit harder without an amplifier. Some phonons will be absorbed instead of redshifting. That energy also has to be accounted for. Yes, so some photons are absorbed instead of redshifting, but the difference in energy between a photon coming in and being completely absorbed and the photon coming in and doing what's called inelastic scattering. So elastic scattering is, here's your crystal. You have elastic scattering where it comes in and then bounces off and it doesn't lose any energy. It doesn't deposit any energy. Like it comes in at the wrong energy to create any excitations or anything like that. So that's elastic scattering. Inelastic scattering is it comes in at one frequency and it leaves at a different frequency. And so that's Raman spectroscopy, is inelastic scattering. Inelastic meaning that it deposits some energy into the system instead of keeping all the energy to itself. And then you could have something come in and just get absorbed directly. And that would create even more phonons. But there we go. Okay. So that's, what's the plan? That's what I got for today. The plan is, thank you everybody for coming in. Appreciate it. So for those who are new to my stream, my name is Jason Stephan. I am a physics professor at the University of Nevada, Las Vegas. We're working our way through the AP physics curriculum now because it just seemed like an interesting thing to do. But I stream physics, I stream astronomy, I stream physics and astronomy. I do some history streams. Occasionally, it's been a while since I've done a history stream, but I do some of them. It's a conversation topic that comes up all the time. I stream on Tuesdays and Thursdays at noon Pacific time. Tuesdays and Thursdays at noon Pacific. So the next time I'll be on is Thursday at noon, where we will be covering what? What are we going to be covering on Thursday at noon? Thursday at noon, we'll be doing radioactivity and nuclear physics. nuclear physics. So this might actually take a couple sessions to do nuclear physics, because nuclear physics we'll do regular nuclear physics to start with, and then we'll move on to nuclear energy, because it's my stream and I get to cover nuclear energy whenever I want. So we'll do a stream on nuclear energy and stuff like that. So that looks like the next couple streams will be taken up in nuclear physics, and then these medical applications, so like nuclear medicine, how these different things work, how PET scans and CAT scans work. I'll need to read up on that. It's one of those things where I always have to read it and then to remind myself how it works. And then particle physics, we've already done some particle physics, but we'll go into more detail with particle physics. And then cosmology and stuff like that, so we'll do a cosmology stream. So it looks like I've got probably another 6 weeks or so, 4 to 6 weeks of content for this AP stuff, and then I'll have to figure out something else to do. So that might be something for me to think about, is what else am I going to do? We haven't yet done all of the possible physics experiments. Like, we put physics experiments on hold for a bit, so we'll go back to doing some of the cool physics experiments that are out there. And then anyway, so I have plans. I thought this would take longer to go through, but it turned out to go pretty quickly. So I'll need to come up with something once November gets here, or probably once December gets here. I'll need to have some new thing that I'm going to go on to. Not sure what it is. Anyways, that's what I do. That's who I am. Last thing I was wondering, how are these vibration modes created? Since you usually think of electrons absorbing and emitting photons, creating mechanical motion from EM force. Okay, so how do you create the mechanical motion? Basically, what you have is you have an oscillator. So this crystal structure is an oscillator, right? Here's this thing. You can think of it as like a wave on a string, except instead of being fixed at either end, so it's got a set of quantum states. A wave on a string has a set of quantum states available to it, like this. In this case, it's a bar that's not attached on the ends. So the ends are free to wiggle, which means that the nodes are going to appear like this. So the lowest energy state here is going to look like that. Okay, it's kind of like an organ pipe. The next highest energy level is going to look like that. Is that right? Yeah. So the next highest energy level is going to look like this. The one above that is going to look like this, I think. Okay, so this is the oscillation amplitude as a function of position. It's going to look like that. So these are all allowed vibration states. They each have some energy associated with them. How much energy does it take to excite this state versus this state versus this state? Okay, so then the photon comes in. It's going to interact with the electrons, because that's what photons do. And if it interacts with an electron that's thermally moving in some direction with the right kind of properties, then it will couple, and the energy will be, some energy will be taken from the electromagnetic field and put in, because when light scatters off of something, it scatters off of some charged particle. So you get a direct coupling between the photon and the electrons, and then if that coupling has the right energy, then it can cause these modes to be excited. Whoops, these modes to be excited, these different things. So that's how you can convert energy from the photon coming in, and then it gets absorbed by the coupling, direct coupling to the electrons. And now the electron recoils. So the electron on one of the atoms, here's this one atom, the photon comes in, interacts with that one atom, and that atom recoils. And if it recoils in the right direction with the right velocity, then it can excite that oscillation mode.